Hello friends, in this session we would be discussing about corrosion of metal containers, about corrosion, what is corrosion, how it occurs, the different factors which are affecting the corrosion and the different methods by which it can be prevented. Metal cans are considered to be important materials for packaging of foods, combining properties of strength, toughness, ductility and impermeability. However, the structure of metals, which gives them their valuable practical properties, is also responsible for their main weakness or susceptibility to corrosion. Corrosion is the chemical reaction between a metal and its environment. It is a universal process affecting all metals to greater or lesser extent. Because the reaction takes place at the metal surface, the rate of attack can be reduced and controlled by modifying the conditions at the attacking surface. Metals are chemically reactive and can be readily oxidized by oxygen to form useless corrosion products. This vulnerability to oxygen explains the fact that, with very few exceptions like copper, silver and gold, metals do not occur naturally in the metallic state but are normally found combined with oxygen or sulfur in their ores. Substantial amount of energy is required to extract metals from their ores, and the reverse process is strongly favored as the metal reverts back to its natural state. The rate of return will be, of course, depend on the environment and the conditions prevailing around the metal. All foods interact with the internal surface of the can in which they are packed. The most common form of this interaction is normally corrosion. In plain tin plate containers, this takes the form of etching or pitting corrosion, and staining of the surface may also occur. But internal lacquers are available which reduce this effect by providing a barrier between the food and the metal wall. It also allows the use of other forms of metal containers like tin free steel or aluminium, which would otherwise be corroded very quickly. In the unlacquered form, only tin plate has some corrosion resistance to the acids found in foods. All other metals must have to be lacquered. Even tin plate must be lacquered where particularly aggressive products are packed, such as tomato puree, or where there is a danger of pitting corrosion or surface staining. Electrochemical corrosion. The reaction of metals in aqueous solutions or under most conditions, also known as wet corrosion, is electrochemical in nature, including the transfer of electric charge across the boundary of metal surface and its environment. An electrolyte is a medium which conducts electricity by movement of ions. The cations like Fe2 plus and anions like chloride moving in opposite directions. When an electrode reaction takes place at a metal surface, the electron flow in the metal corresponds to an ion flow in the electrolyte. When a metal corrodes, atoms of the metal are lost from the surface as cations, leaving behind the requisite number of electrons in the body of the metal. This dissolution of metal is called an anodic reaction and takes place at an anode. The anodic reaction always involves the release of electrons or electrochemical oxidation. Simultaneously, reagents in the electrolyte solution react with the metal surface to remove electrons left behind by the departing metal ions. This removal of electrons is termed as cathodic reaction and takes place at a cathode. The cathodic reaction always involves consumption of electrons or electrochemical reduction. Since practically all metals are covered with an oxide film, this must be removed before the metal can be exposed to an electrolyte. A metal covered with an oxide has a different properties in a solution from a bare metal. But in studying electrochemical corrosion, it is simplest to begin with the ideal case of a pure bare metal electrode on which the only reaction occurring is metal dissolution. Now we will see the different factors that affect the rate of corrosion. First one is polarization of the electrodes. When current flows, there is a change in the potential of electrode. This is known as polarization. As the current begins to flow, the potential of cathode becomes increasingly negative and the anode is increasingly positive. Consequently, the potential difference between the anode and the cathode decreases until a steady state is reached, when corrosion proceeds at a constant rate. Thus, the corrosion current and therefore the corrosion rate will be affected by anything which affects the polarization of the electrodes. Next factor is supply of oxygen. The rate at which oxygen is supplied largely governs the rate of corrosion. Since corrosion by oxygen reduction requires the presence of oxygen for the cathodic reaction to proceed, the rate of supply is proportional to the rate at which oxygen diffuses to the metal surface, and this depends on the concentration of dissolved oxygen in solution. This is the justification for the practice of attempting to remove all the oxygen from the canned foods prior to seaming on the can end. Another factor is temperature. The rate of corrosion generally increases with increase in temperature as more reactant molecules or ions are activated and are able to cross over the energy barrier. As well as increasing the temperature have a tendency to increase the rate of diffusion of molecules or ions in a solution, although the solubility of oxygen in water decreases with increasing the temperature. Next factor is passivation. Passivation refers to a material becoming passive, that is, being less affected by environmental factors like air and water. Passivation involves a shielding outer layer of corrosion which can be applied as a micro coating or which occurs spontaneously in nature. As a technique, passivation is the use of a very light coat of a protective material such as metal oxide to create a shell against corrosion. If the metal can be oxidized to an oxide that is stable in the electrolyte, then the metal is called passivated. Passivation usually requires strong oxidizing conditions. Thus, corrosion resistant metals and alloys can withstand an aggressive environment because of the presence of thin films of adherent oxide on their surfaces. The oxide layer will completely stop the anodic reaction, which is the direct cause of corrosion. And if the film is insoluble in electrolyte solution, it will form an insulation barrier which will reduce the rate of cathodic reaction. Iron is readily attacked by dilute nitric acid but is inert in concentrated nitric acid because a thin protective film is formed. As a result, iron behaves in concentrated nitric acid like a much more noble metal or non-reactive metal than it actually is. Iron can also be passivated by chromate solutions, as can tinplate, the latter being a very important step in the manufacture of tinplate. Passivation of tin plate can be achieved using an aqueous solution of chromic acid. Although an electrolyte treatment in a sodium dichromate electrolyte has gained widespread favor, the resultant film is composed of chromium and chromium oxides and tin oxide. Its properties vary depending on the quantity and form of these basic components used. Now we will see the corrosion of tin plate cans. The tin plate surface consists of large area of tin and tiny areas of exposed tin iron alloy and steel as a result of scratches in the tin coating. Hot dip tin plate has a considerable tin iron alloy layer. Electrolytic tin plate has a much thinner layer which is electropositive to the base tin, thus acting as chemically inert barrier to attack on the steel base. The effect of this barrier is to prevent a significant increase in the steel cathode area. Thus, the density of degree of continuity of the alloy layer has a material effect on the rate of corrosion. In the case of tin plate exposed to aerated aqueous environment, tin is noble to iron according to the electrochemical series. Therefore, all the anodic corrosion is concentrated on the minute areas of steel and the iron dissolves, or we can say it rusts or corrodes. In extreme cases, perforation of the sheet may occur. This is the process which occurs on the external surface of tin plate containers. But inside a tin plate can, the tin may be either anode or cathode depending on the nature of the food being packed. In a dilute aerated acid medium, the iron is the anode and it dissolves, liberating hydrogen. In de-aerated acidic food, iron is the anode initially, but later reversal of polarity occurs and the tin becomes the anode, thus protecting the steel. Tin has been described in this situation as a sacrificial anode. This reversal occurs because certain constituents of food can combine chemically with tin or Sn2 plus ions to form soluble tin complexes. As a consequence, the activity of Sn2 plus ions with which the tin is in equilibrium is greatly lowered and the tin becomes less noble, that is more electropositive than the iron. The corrosion in de-aerated acidic food cans comprises three stages. During the first stage, oil and tin oxide layers are removed from the can surface and the speed of tin dissolution is high. This stage continues for 4 to 15 days depending on the nature of the food. The mirror surface of the tin coating should change to one in which the shape of the individual tin crystals may be seen with the naked eye. In the second stage, the corrosion speed is slow and almost constant. Continued dissolution of the tin causes broadening of the existing pores and scratches, uncovering more and more alloy layer and the steel. The unprotected steel provides sites for cathodic reaction and the developed hydrogen is taken up by the depolarizers in the food. The area of exposed steel dictates the rate of hydrogen evolution, and as the ratio between the areas of tin and steel decreases, that is, as more steel is exposed, polarization decreases. This stage is slow and can last for over 2 years. The third stage is shown by high rate of tin and iron dissolution. As large areas of steel is exposed, hydrogen produced at a faster rate and accumulates in the can, causing swelling. Once the internal pressure in the can causes the ends of the can to bulge, which sometimes thought as the microbial spoilage, but actually it is due to production of hydrogen. So the bulge causes the product to be no longer sellable, as the swollen can normally people think as microbial spoilage and not the hydrogen evolution. As well as the metal contents of the food may have reached an unacceptable level by this stage. Therefore, this third stage is of little importance, since by then the food will have reached the end of its acceptable shelf life. So the first and the second stage, if it is prevented, then it can prevent the corrosion. 4 different scenarios are possible in plain tin plate cans, depending on the nature of the food and the presence of depolarizers. The first is referred to as normal detinning and is an essential process in plain cans of most products. It has already been described in earlier slide as the second stage and leads initially to itching and later detinning of the can. Food products characteristics of this type of corrosion include low pH products like citrus, pineapple, peach and apricot packed in plain tin plate cans. The second is known as rapid detinning. Rapid detinning is caused by the use of tin plate with an tin coating mask that is too light or very thin tin plate coating, or by a product that is intrinsically too corrosive or contains corrosion accelerators such as dissolved oxygen or anthocyanins, which are chemically reduced. Food products characteristics of this type of corrosion includes tomatoes and aggressive citrus products like lemon juice as well as certain berry fruits. The third type can be best described as partial detinning and pitting. Early failure occurs because of hydrogen swelling and perforation as a result of the exposed steel continuing to corrode. This type of behavior is associated with products such as prunes or pear nectar or with steel of inferior quality. And the fourth method is described as pitting corrosion, which is a reversal of the normal situation, with iron being anodic to tin. Thus the tin does not corrode, but pitting corrosion of the base steel occurs. In rare cases, pitting corrosion will also occur when the tin is in fact corroding but at too slow a rate to provide sufficient electrochemical protection to the exposed steel. Pitting corrosion used to be rare, appearing in highly corrosive products such as pickles and carbonated beverages formulated with phosphoric acid. However, it is becoming more common and it is the major cause of failure in canned pears and pear products, which are highly acidic in nature. Now we will discuss about corrosion of enamelled cans. Food cans with enamel or lacquer coatings are used to protect against excessive dissolution of tin, sulfide staining, local itching, and change in color of pigmented products such as berry fruits. However, the use of enamel will not guarantee the prevention of corrosion and in some cases may actually accelerate it, or it may faster the reactions. Therefore, careful consideration must be given before selecting an enamel for a particular canned food. The general pattern of corrosion in enamelled can is very different from that which is found in plain cans, and it is generally more complex. The only exposure of metal in an enamelled can is at pores and scratches in the enamel coating and at the cracks along the side seam. Some of these discontinuities in the enamel coating may coincide with pores in the tin coating, thus resulting in exposure of the steel, even if defects in the enamel film expose only the tin coating, the availability of all the corrosion promoters in the can for attack on the limited areas of tin ensures that steel is soon exposed to them. Thus, it is easily possible for the use of enamel to actually reduce the shelf life of canned product. So, the enamels generally applied for the betterment of the cans can sometimes harm the cans or can start the corrosion in the cans. Ions are electrically charged. Their transfer through the enamel coating is complex and depends not only on their electric charge but also on the concentration of the electrolyte. If the transport rate of cations and anions through the coating differs, the coating itself may become charged. Thus, the protection offered by the enamel coating depends on its resistance to ion transfer, which may take place even in the absence of pores, scratches, or blisters. The performance of enamelled food can is greatly affected by thickness of the enamel coating. A thickness of 4 to 6 micrometer is sufficient for non-aggressive products like apricots and beans. But aggressive products like tomato paste require thickness of 8 to 12 micrometer. The heavier coatings having much lower porosities. Failure of enamelled can is often due to a reduction in the bond between the enamel and the metal surface, resulting in subsequent lifting of the enamel coating or removal of enamel coating. Thus, good adhesion is required to prevent anodic reactions, to counteract forces developed under the coating due to physical or chemical factors, and to ensure an aesthetic appearance. Loss of adhesion may begin prior to corrosion due to stresses during fabrication or during processing. But typically, detachment of the enamel coating is a result of breakdown taking place through or under the coating or to under the film corrosion spreading from exposed metal. The quality of surface of the tin plate prior to enameling has a major effect on the adhesion and enamel performance. The presence of salt residues can cause failure due to their ability to attract water and therefore establish a conducting film beneath the coating and to provide ions for carrying the corrosion current. Now we will see the corrosiveness of different food products. The most important corrosion accelerators in food includes oxygen, anthocyanins, nitrates, sulphur compounds, and trimethylamines. From a corrosive point of view, it is convenient to divide foods into 5 classes: those that are highly corrosive like apple and grape juices, berries, cherries, prunes, pickles, and sauerkraut; those that are moderately corrosive such as apples, peaches, pears, citrus fruits, tomato juice, etc., and those that are mildly corrosive like peas, corn, meat, and fish, and strong deteners such as green beans, spinach, asparagus, and tomato products. Beverages are conveniently considered as a 5th class. While the above classification offers a good broad guide, it is important to note that different lots or varieties of same food can exhibit as much variation in their corrosiveness as may exist between different types of foods. Thus, for example, the same variety of fruit from different growing regions may vary several fold in corrosiveness. The various factors that can influence the corrosiveness of food products and beverages will now be considered in more detail. And of that, the first one is acidity and pH. No direct proportionality exists between the acidity of a product and the degree of corrosion of tinplate. In other words, two products of the same acidity will not necessarily be equally corrosive. It also appears that pure solution of organic acids are less corrosive than the fruit juices containing them, suggesting that fruit juices contain unidentified depolarizers which enhance the corrosive action of the organic acids. It has been well established that the tendency of an acid to form a complex with dissolved tin has an important bearing on the relative polarity of tin and steel, and hence the degree of corrosion. The type of organic acid is more important than its concentration, and the addition of nitrate increased pitting severity in all acid solutions. If you see the pH, same as acidity, no direct relation exists between pH and the degree of corrosion of tinplate. This is not surprising when it is considered that the reaction product when a metal is dissolved is not always an ionic species but often a solid oxide or hydroxide. The pH of the system also determines the relative cathodic protection given to the steel. In some cases, tin is cathodic to steel over a certain pH range. For example, in the case of acetic acid, the range is pH 2 to pH 4.5, while in others, it offers protection up to pH 4. Above that level, it may accelerate the corrosion. Another component is sulphur compounds. Sulphur and sulphur compounds may be introduced into the can in a number of ways: as spray residues from agricultural chemicals, as a residues from sulphur containing preservatives, and as components in sulphur containing compounds such as proteins in meat, fish, and certain vegetables. The proteins are degraded during heat processing, releasing free sulfide or hydrosulfide ions and evolving hydrogen sulfide gas into the heat space. Trace amounts of sulphur compounds from agricultural chemicals can lead to accelerated corrosion and failure of plain tin plate cans containing acid foods such as apricots and peaches, as well as pitting corrosion can occur, and this has been attributed to inactivation of the tin coating by a protective film of sulfide having more cathodic potential. As a consequence, there is a significant reduction in tin dissolution rate and no electrochemical protection of the steel by the tin. Sulfur dioxide may be directly reduced on the tin surface to sulfide or even to sulfur, with tin passing into solution and the development of unpleasant odors and flavors. Residual sulfur dioxide accelerate corrosion through its action as a depolarizer. Trace amounts of sulfur dioxide as low as 1 milligram per kg are sufficient to accelerate corrosion. Such corrosion problems may be overcome by the use of enamelled cans. There are two types of sulfide: iron sulfide staining, also called sulfide black, and the other involves tin sulfides. Neither type constitutes a health hazard nor leads to failure of the can, but both types may cause adverse reaction from the consumer, as they can give some pigmentation in the food products. Iron sulfide stains are characteristically black and usually occur in isolated points on the can, like headspace, during immediately after heat processing. Iron sulfide is not formed as pH values below about 6, so that it is uncommon to find it in the portion of the can in contact with the contents. The problem may be overcome by using enamelled cans or plain cans with enamel ends. Tin sulfide staining is usually widespread throughout the can and is a blue, black, or sometimes brown pigmentation. Two stages are believed to be involved: an oxidation of the tin followed by deposition of an insoluble tin sulfide precipitate on the surface. This occurs during or soon after heat processing and shows little or no increase in the intensity during the storage. It may be reduced by using sulfur resistant enamels into which quantities of zinc oxide or carbonate are added before being applied to the plate surface. This reacts with sulfur bearing gases to form almost invisible or white zinc sulfide pigments, which are generally not objectionable by the consumers. Next class is nitrates. They are found in fruits and vegetables grown in heavily fertilized soils. Vegetables such as green beans, spinach, turnips, lettuce, beets, radishes have been shown to contain occasion several thousands milligrams per kg of nitrates. Nitrates are very efficient cathode depolarizers since they are capable of being reduced all the way to ammonia. They have been responsible for serious economic and toxicological problems in some canned foods, notably tomato products. Although nitrates and nitrites are also present as intentional additives in processed meats, they present no problem. This is because meat products are above the critical pH range of 5.5 for detinning to occur via the nitrate tin reduction system. The reduction of 60 mg of nitrate could account for dissolution of 470 mg of tin. A tin coating of 11.2 GSM may be dissolved completely within 6 months by tomatoes containing 100 mg per kg of nitrate. Overcoming the problem by restricting the use of nitrate fertilizers has proved difficult. It is also possible to avoid the use of waters with a high nitrate content for canning operations. A suggested maximum is 5 mg per liter nitrate. The best solution to problem at present is the use of enamelled cans, although the development of corrosion inhibitors would offer an alternative solution. Now we will talk about certain plant pigments, and the first one is anthocyanin. Anthocyanin and related pigments are among the most important potential corrosion accelerators since they are easily reduced. Anthocyanin pigments can also act as anodic depolarizers through their ability to form complexes with cations, particularly those of iron and tin salts. Analysis of samples of canned fruit after a period of storage usually shows a greater amount of tin in the drained fruit than in the syrup, indicating that at least part of the tin is combined in an insoluble form with some constituent within the fruit. The nature of the anthocyanin pigment is also important. For example, raspberries contain cyanidine glucosides, which have orthodihydroxy groups in their structures. It is these groups which are involved in the formation of blue tinted complexes with metals such as tin. The major pigment of strawberries is pelargordin 3 glucoside, which does not possess the necessary orthodihydroxy groups for complex formation. Therefore, strawberries do not show the same shift to a blue color in the presence of tin salts as do the raspberries. Combination of metal ions with tannins has been observed in other fruits. For example, discoloration of canned cranberry has been attributed to the formation of complex between tannins present in the fruit and the tin salts. It should be noted that not all reactions between the plant pigments and the metal ions will produce undesirable colors, although this is usually the case with anthocyanin pigments. Synthetic colorings can also have an effect on corrosion of tin plate containers. The canned products which most commonly contain synthetic colorings are soft drinks, which consist basically of sugar-based syrups and carbonated water containing flavors, acidulants and colors. The behavior of soft drinks depends on a considerable extent on the presence of azo dyes and the amount of residual oxygen in the filled can. Both of these components are capable of acting as corrosion accelerators and are potentially active corrosive agents. Tin dissolution may adversely affect the color of some products, and iron dissolution may lead to perforation and flavor defects. Thus, fully enameled cans are essential for the products which are generally manufactured with synthetic food colorings. Now we will see the effect of processing and storage on corrosion of metal containers. Removal of as much oxygen as possible is an essential part of good cannery practice, and a variety of methods are used: hot filling, vacuum filling, exhausting, closure under vacuum, steam flow closure, and vacuum syruping. As well as positive control of the headspace volume is also essential. A larger headspace is likely to contain a higher residual oxygen concentration than a smaller one. However, the larger the headspace, the more room there is for accumulation of hydrogen resulting from corrosion, and thus the greater the time required to form a hydrogen swell. Despite the above procedures, there will always be some oxygen present in the headspace of newly filled cans. The rate of oxygen consumption at this stage is quite rapid but decreases with time. The oxygen acts as depolarizer, accelerating corrosion by reacting with the hydrogen formed in the can through a cathodic reaction. If the residual pressure in the headspace of a filled can of a common size is 0.5 atmospheres, then the oxygen present would be capable of removing about 0.25 GSM of tin from the coating, producing 15 mg per kg of dissolved tin in the can contents. Although this is relatively small amount in comparison with the total coating weight, the action of the oxygen may be localized on a narrow zone of the gas or liquid interface in the headspace. This may result in the production of an unsightly east line, even exposure of an area of steel much larger than that exposed at pores in the initial coating. Thermal processing. Very little is known about the effect of heat sterilization process on corrosion rates, except that the quantity of metal dissolved during the process is very small. This is hardly surprising given the comparatively short processing times relative to the total shelf life of the can product. However, degradation products formed during thermal processing can cause corrosion. Example, non-enzymatic browning intermediates and sugar derivatives. What has been emphasized is the importance of correct cooling. Failure to cool cans adequately can lead to increased corrosion, since the can center temperatures may take several days to return to the ambient temperature. On the other hand, cooling to too low a temperature may cause paneling of the can walls as well as external corrosion, since complete drying of the can exteriors will not occur. Conditions of storage temperature has also effect on the corrosion. The rate of a chemical reaction increases as the temperature is raised, and for many reactions the rate doubles for each 10 degree centigrade increase in the temperature. Thus, to minimize undesirable reactions such as non-enzymatic browning in canned foods, it is preferable that the storage temperature be kept as low as possible. Now we will discuss about the external corrosion of cans. Tinplate rusts readily in the presence of moisture, rusting occurring more readily the thinner tin coating. The presence in the atmosphere of sulfur dioxide or oxide of nitrogen accelerate the rate of corrosion, since they dissolve to form acids. Chlorides can also cause a rapid increase in the rate of corrosion. Under normal conditions, on the outside of a can, tin is cathodic to iron, and when a galvanic cell is set up at pore sites, the attack on the iron is accelerated by presence of tin. Rust forms as a result of corrosion of iron. Three stages of exposure to the risk of external rusting may be differentiated: thermal processing, cooling of cans, and storage. So in the first stage, during thermal processing, the essential ingredient for rusting of cans during thermal processing is presence of oxygen in the processing vessel. When cans are processed in water at atmospheric pressure, as is quite common for high acid, low pH products such as fruits, the risk reaches a maximum at a temperature of about 80 degrees centigrade. Above this temperature, the loss of dissolved oxygen counteracts the acceleration of the reaction rate at the higher temperature. Therefore, when full boiling is not required, the water should be deoxygenated and preferably treated with corrosion restrainers. When cans are processed in steam, it is important that proper venting of the retort occurs so that all the oxygen initially present is dispersed off from the retort by the steam, as well as minimizing any external corrosion. The removal of air from the retort prevents pockets of air from surrounding individual cans and insulating them from the steam, the latter situation leading to underprocessing. The addition of additives to steam or water used in thermal processing has been investigated as a possible way of minimizing the external rusting of cans. Although promising results have been obtained with soluble or volatile oils which form a water repellent film on the metal surface, the cans take on an oily appearance and feel, and difficulty can be experienced with adhesion of paper labels after processing of the food. Second stage is cooling of cans. So the cans are typically cooled after thermal processing by passing water through the retort or placing the cans in a cooling canal. But in some canneries, hot cans are removed from the retort and left to cool in the air. If cans are cooled with water, it is a regulatory requirement in virtually every country that such water contain a measurable amount of bactericide when it exits the retort. This usually means, in the case of chlorine, that incoming water has a free chlorine content of around 5 to 10 mg per liter. When cans are water cooled, they should be around 40 degrees centigrade when they are removed from the retort. If they are warmer than this, there is a risk of thermophilic spoilage, chemical degradation, and significant internal corrosion. If they are cooler than this, insufficient heat will remain to evaporate any water adhering to the exterior of the can. Cans should be stacked in such a way so that to enable self-drying to occur prior to labeling and packing. Accelerated drying methods such as the use of hot air or steam spray or rolling cans over sterile absorbent surfaces have advantages in minimizing the external corrosion of cans. If the corrosion is to be prevented during storage, then the atmosphere surrounding the can must be free of corrosive vapors or chemicals and not promote condensation of moisture. As well, packaging materials in contact with the cans should be as free as possible from soluble chlorides, sulfates, or other salts which may promote condensation of moisture and corrosion. Cartons usually have a water content of 10 to 12%, and when the air temperature rises, moisture evaporates from the cartons in the warmer outer zone and condenses in the cooler center of the stack. The shrink wrapping of cans while protecting them from promoters of corrosion found in the atmosphere, can cause problems of condensation if the air inside the shrink wrap contains a considerable quantity of water vapor and the package is later subjected to a drop in temperature. Rusting can also be caused by unsuitable conditions of transport and storage where sweating occurs. This is especially so when cans are transported from temperature to tropical areas or temperate to temperate areas via the tropical areas. Attempts to prevent condensation of moisture by free movement of air have usually been unsuccessful because of the center of the stack of cartons filled with cans take a long time to respond to the external temperature change and may remain below the dew point for longer periods. The use since the 1970s of bulk shipping containers, each holding about 18 tons of cans, has become increasingly popular for sea transport. Such a container may include 2 tons of carton material. If the moisture content of such material changes from 12 to 10, 45 liters of water would be released within the container. Such a change could come about if the upper part of the container were exposed to the sun, causing the water to distill from the warmer to the cooler parts of the container. Despite such possible hazards, the use of large containers makes it much easier to apply measures needed to avoid rust promoting conditions. Now we will see the corrosion of other types of cans, like the cans which are not tin plate containers. The first one is ECCS cans or chromium coated cans. Although the chromium or chromium oxide layer on ECCS cans is only approximately 1/5 the thickness of typical tin plate coating, transforms the base steel into an excellent can making material by providing rust protection, outstanding enamel coating adhesion, good resistance to corrosion, and good resistance to under-film sulfide staining. 2-piece ECCS cans have significantly lower product iron contents compared with 3-piece tin plate cans. Aluminum cans rapidly forms a protective oxide film when exposed to air or water. The film is extremely thin, of about 10 nanometers thickness, but it renders the metal completely passive in the pH range from 4 to 9. Because aluminum oxide is amphoteric, it will dissolve in acid or alkali to give the soluble aluminum cation or anion respectively. In practice, it is found that aluminum will corrode in acid solutions pH below 4 and alkali pH above 9, but its corrosion resistance is excellent in the range of pH 4 to 9. Having a strongly negative electrode potential, aluminum is liable to undergo severe corrosion if brought into metallic contact with copper, iron, or other more positive metals in the presence of electrolyte. For example, fruit juices. Thus, care must be taken to ensure that situations which could lead to such corrosion are avoided. Although no foods have a pH greater than 8, cleaning solutions used in food processing plants frequently have pH values of up to 13. It is therefore important that these solutions do not come into contact with aluminum packaging materials and that any package contact surfaces which are cleaned with these solutions are thoroughly rinsed with water afterwards. So friends, to conclude this session, we may say that the corrosion depends on many conditions like the type and the material of the containers, the storage conditions, the processing conditions, even the experience of the packer, how he or she is actually packing the cans is also important. And nowadays actually there is no specific method to prevent corrosion is available. So what we can do is we can just use the more and more enamelled cans which can avoid the favorable conditions for corrosion, and there is a little research has been done on use of anti-corrosive agents to be used in the lacquers or in the container material itself, but this research is still in the stage of infancy. Thank you.